thanks. It's nice to be here today. I know you've gotten a lot of other talks about different aspects of climate change this week, so some of what I say, and certainly the beginning might be a little redundant, but it doesn't hurt to hear it again. And the most obvious one is probably the first slide here, which is the Earth is warming, right? But it's not just warming uniformly. There are some places where it's warming more than others. In particular, it's warming in the Arctic faster than the global average, and that's where all our ice is. And so the simple part of the sea level story is you melt the ice, it goes in the oceans, and it raises sea level, right? It's more complicated than that, but that's certainly one of the messages. And that warming in the Arctic is it's not just abnormal globally, but it's abnormal over the past 2,000 years. So this is a reconstruction of Arctic temperatures over the last 2,000 years. You can even see, up until 100 years ago or so, it was cooling, and that was a natural cooling that was just due to the variations in the Earth's orbit about the sun. But then the warming kind of even overtook that cooling, and now we've seen quite a bit of warming in the Arctic. And then also the Antarctic's warming, especially Western Antarctica, because it's lower than Eastern Antarctica. And so we're starting to see some responses there as well. And so I'll show you some of the evidence of this. How I got into this is actually through the satellites. I use satellites to study the Earth. I didn't initially start out in working on sea level change. I was kind of got into it through analyzing satellite data, and it kind of led me down this path. So let's start out with a little introduction to sea level change. And then I got two slides here that kind of illustrate this. But the first one in here is what causes sea level to change. So obviously the one I just alluded to was the melting of ice. You got ice on the land, you melt it, and it runs off into the oceans, and it raises sea level. Another one that's a major factor is as the water in the ocean warms, so as heat goes into the ocean, and the water then expands in a phenomenon we call thermal expansion, but it's just like the expansion of mercury in a thermometer. So the water expands, and so the volume of the water increases and sea level goes up. There's also, you have changes in terrestrial water storage. For instance, if you build a reservoir on the land and put water into it, effectively you're taking water out of the oceans and putting it onto the land, which is negative sea level rise. And that's been a factor here in the last 50 years or so as we've built reservoirs on the land. Not a major factor, but it's still a factor. And then the last one I'll mention here, it talks here about subsidence along the land and land movements in general. So this isn't what I would call actual sea level change because it's not changing the volume of the water in the oceans. But nevertheless, if you're living in New Orleans and the land is subsiding, you're going to see sea level go up even though the volume of the water is not changing. And so for kind of the social impacts, economic impacts, it's still a factor. And I'll get back to that at the end of the talk. But all this can be summarized in our little bathtub model here, which it's amazing. Everybody from experts in the field to school children seem to like this model. So we can all relate to it, right? We have water coming into the oceans from precipitation and from runoff from the continents. So it rains over the ocean and water goes in and changes the volume. And then water runs off of the continents down rivers and streams and into the oceans. So we got water coming in, that's kind of a continuous process, right? And then we have water going out from evaporation. So it evaporates from the oceans, goes into the atmosphere, and then gets reprecipitated over the continents. So that's kind of the global water cycle, which is another idea you can kind of fold into the sea level story. Is the sea level change is really all about changes in the global water cycle and these balances that I'll talk about. And then if you introduce a heat source, then sea level will go up just through that phenomenon of thermal expansion. And that's not necessarily globally uniform. You can have some areas of the ocean that warm more than others, and so sea level will rise quicker there than in other places. Some places the ocean may be cooling and sea level will go down. And then if we introduce an ice sheet on the side here, watch what happens to the water. See how it goes up near the ice sheet? This is a phenomenon I'll get to again at the end of the talk. But it's basically that all that mass on the edge of the ocean gravitationally pulls the water up towards that mass. And so sea level is a little higher around the ice sheet, just due to that gravitational attraction from the mass of the ice itself. So then when you melt the ice, water goes into the ocean, it raises sea level, but it turns out, of course, when you melt the ice, sea level falls in the vicinity of the ice sheet because that gravitational effect goes away. So as I'll show you on a slide later, if you melt an ice sheet, there's actually very little sea level rise near the ice sheet. It's like melting ice in Greenland. If you live on the coast of Greenland, you're not going to see much sea level rise. And yet, if you live far away from Greenland, you're going to see more than you would expect. This is an interesting phenomenon. I was talking to a group of Norwegians a month ago, and I commented to them that they want it, if ice is going to melt, they should hope it's Greenland because it won't affect them as much as, say, Antarctica, which kind of doesn't make sense because Greenland's closer to Norway, but that's how it works. So let's talk a little bit about icebergs and sea ice because I know you've heard a little bit about this week. So what about icebergs and sea ice? Well, they don't affect sea level if the ice is already floating in the oceans. And that's just Archimedes' principle that the amount of water that's displaced by the ice is equivalent to the amount of water in the ice. So once the ice, if there's any, let's say you have ice on the continent, it calves off and goes in the ocean, it's already caused all the sea level rise it's going to cause. So and again, that's just, you can do simple experiments in class with things like this demonstrating Archimedes' principle. So if you look at where the ice is in the Arctic, of course you got a lot of sea ice here, but that's all floating on the oceans. So while melting that ice can cause changes in salinity and other things that have small effects on sea level, there's no major impact there. The ice that we're concerned about is the ice on the land, in particular here, the ice in Greenland. So even though, I'm sure you've heard about the decline in the sea ice and how precipitous it's been. And while this is something even I look at as a sea level scientist, because I think it's, again, the canary in the coal mine idea, it's not an indicator of sea level change, even though it's a very important climate effect. So I think we need first to find what global mean sea level change is. It may seem kind of obvious from the words here, but it's the change in the average height of the oceans of the entire globe at any single point in time. This is a snapshot of sea level that was determined from satellite altimeter data, and the scale here is about plus or minus 20 centimeters, and sea level changes a few millimeters a year, so global mean sea level. So the average here is important. You're going to see a lot of departures from the average, and so the average is just a way of telling you, kind of giving you a global number that tells you how things are changing in an average sense. So usually all the plots I'm going to show you units of millimeters. And so just to remind you, 25 millimeters is an inch. Also, we're not including here in the discussion the effects of ocean tides. And you can have ocean tidal effects that are many meters on top of the global mean sea level effect. And then also doesn't include things such as storm surge. So now sea level rise can certainly affect storm surge because the storm surge is going to be starting from a higher level. And certainly if you're living on the coast, one of the first ways you're going to experience sea level rise is probably from a storm and not the actual rise itself coming over the levee or whatever. So, but that's not going to be part of the discussion today. So you have to add these effects, tides and storm surge, on top of whatever the global mean is you're starting at. So that's just a definition of mean sea level there. Now let's look at what these different contributions are and how big they could be. So I talked about thermal expansion. Even in the worst climate change scenarios, the most sea level rise you're going to get from thermal expansion is about a meter, say in the next few hundred years. So that's just taking the climate model projections and taking the worst case scenario. On the other hand, mountain glaciers, if you melt all the remaining mountain glaciers in the world, this is outside of Greenland and Antarctica, then you would raise sea level by about 3/4 of a meter. And then you look at Greenland. If you melt the whole Greenland ice sheet, it's 6 to 7 meters of sea level rise. Now, most people think that would take, 1,000 years or more to melt the whole ice sheet, but even melting a fraction of the ice sheet could result in significant sea level rise. And same thing with Antarctica. There's 60 meters of potential sea level rise tied up in the ice in Antarctica. So when you think about, a meter of sea level rise is a lot, but when you think about kind of catastrophic outcomes, it's Greenland and Antarctica that we have to be concerned about. So when I think of catastrophic as multiple meters of sea level rise. So, and then I also mentioned land water storage. Those effects are thought to be quite small, but we also don't have a real good handle on what it is right now. Now, can this happen? And I like to put this plot up because it says, yes, it could, because it happened before. It happened about 125,000 years ago. Back at the last interglacial, when the Earth was about as warm as it is now. It was a few degrees centigrade warmer, but that's kind of where we're heading. And during that time, sea level was about 6 meters higher than it is today. So you don't have to ask yourself if these things are possible. They've happened before. Now, obviously, 125,000 years ago, this was due to natural variations in climate, Earth's orbital variations about the sun and other effects. Whereas the increase that we see today, we believe is being forced by us, obviously, due to the CO2 effects. I didn't put a plot in here, but you can put up a plot of CO2 variations, and it very closely mimics this sea level curve. And so it's easy to make the connection between sea level and CO2, and if you increase CO2, sea level is going to go up, and we know that we're the ones providing the CO2 this time around. Question up front here?
So the zero is where we are today?
Yeah, yes.
So that would be above?
Yeah, so 125,000 years ago, it was 6 meters higher than it is today. Okay. And it was only a few degrees warmer than we are now. Everybody believes that's kind of where we're headed. So now the one thing about this, we call this paleoclimate data, and one thing about this paleo data is that the timing of things is not well determined. So we really couldn't say whether that 6 meters is going to happen in the next 100 years or in the next 1,000 years. So that's the piece they don't know. But it's pretty certain that we're going to see meters of sea level rise. The question is, how long is that going to take? So how do we measure sea level change? Well, one of the ancient ways of measuring sea level change, which we still use today, is tide gauges. And you think of a tide gauge as just a big tube you take to the end of your pier. You put the tube in the water, you put a bobber in the tube, and you watch it go up and down and measure where it is in the tube. And that gives you a measurement of sea level. The only problem with that is that if the land on which your pier is attached moves, then that would cause a change in relative sea level as well, which isn't related to changes in the water. So we have to keep that in mind and correct for those effects if we can. So the techniques that I use in my research are satellite data. You probably heard from Walid about ICEE measuring the height of the ice sheets. So I won't focus on that, but I will talk a lot about radar altimetry, which measures sea level directly, and satellite gravity measurements. So with radar altimetry, you have a radar on board the satellite, which fires a pulse down at the ocean surface. It reflects off and comes back. We measure how long it takes for that to occur. So you take that time and multiply it by the speed of light and divide it by 2, and that gives you the height of the satellite above the ocean surface, which isn't quite what we want, right? We want sea level. So then you have to determine the height of the satellite, say relative to the center of the Earth, using satellite tracking technologies. You subtract off the height of the satellite above the ocean, and that tells you how high the ocean is relative to the center of the Earth. So it's a pretty simple technology in that sense. So let's talk a little bit about tide gauge measurements, then I'll get into altimetry, and then I'll talk a little bit about these satellite gravity observations and tell you how that works. So tide gauge data, this is our link back to the past. So we have, over the last 100 years, we've seen about 1.8 millimeters per year of sea level rise on average. But you can kind of break this plot up. I kind of see 3 different periods here, although scientifically we wouldn't really divide it up this way. But for the first 40 years or so there, it was going up at less than a millimeter per year. And then from about 1920 to about 1980, it was 2 millimeters per year. And then the last couple of decades, it's been going up at 3.2 millimeters per year. So so clearly the tide gauges show us that sea level has been, the rate of sea level rise has been increasing. Now during this last period there, that last 20 years or so, that coincides with when our satellite observations start. So our satellite altimeter data started with the launch of Topex Poseidon in 1992. So here is the results from the satellites, and they're much more precise than the tide gauges because we get measurements everywhere over the globe instead of the tide gauges just being along the coast. So here are those results from the satellite altimetry of the last 17 years from 3 different satellites. And the rate of sea level rise during that period is about 3.4 millimeters per year. And you can see there's also some variations here. For instance, sea level was higher during the 97-98 El Nino event. It was also lower up here when we were in a La Nina. Then it's starting to come back up again. And right now we're in a mild El Nino event right now, and so it's a little bit higher. So you do see variations from year to year, which is mostly, we believe, due to El Ninos. And so you don't want to overinterpret, say this period here, it looks like sea level's leveling off, and we can all go home, right? Our job is done. But then it started going back up again. But you'd be surprised, especially with the, when sea level leveled off here, there were all kinds of skeptics that were grabbing these plots off my website and putting President Bush next to them and having him point at it, and it got a little ridiculous after a while. So, so just beware that this is all this stuff in here, all the internet variations is that's kind of the weather of the ocean, and we have to average through the weather to get at what's happening in the long term. So that 3.4 millimeters per year global average, this is how it's distributed spatially. So this whole map averages to 3.4 millimeters per year, but some places it's been going up at a centimeter per year, and some places it's been going down at a centimeter per year. But on average, it's going up. So in fact, off the coast of California here, it hasn't risen much at all. I was at a conference just a month ago talking to people, planners out there who are studying how sea level rise is going to affect electric utilities and city managers, things like that. And this is, they were surprised that sea level hasn't gone up much along the coast of California, but that's just due to something called the Pacific Decadal Oscillation, and it'll flip back in another decade and things will be going up again. So you can't overinterpret everything you see here, but it is important to note that there are spatial variations. The global mean does not mean it's going everywhere the same. That's just the average. Yes?
What is the, on that previous slide, what is the IB correction?
Oh, I should have erased that. That's the sea level response to changes in atmospheric pressure. And so we try to remove those variations because we don't want, that's kind of the weather in the atmosphere. And we don't want that to, we'd like to remove that effect since we understand it. So we've corrected the sea level here for changes in atmospheric pressure. Now here's the same map or a similar map over a different time period on the left-hand side here. And on the right-hand side, I'm going to put observations of ocean heating. And you can see a lot of the variations that we've seen in sea level are just due to changes in how the ocean has taken up heat, with more warming in the Western Pacific than in the Eastern Pacific. Now, these are in the water measurements. So these are measurements from ships and floats, profiling floats that go around the ocean. And they're not really globally distributed, so we don't have a lot of data here in the Southern Ocean. But where we have data, it looks pretty good that it describes a lot of the variation we see in the sea level measurements from the satellites. I'll just spend a moment on mountain glaciers. They're obviously melting, but the rate of melting is increasing. Starting about 1960, they were contributing about a ½ millimeter per year to sea level rise, but over the last couple of decades, that's been accelerating to almost a millimeter per year. And in fact, the most recent papers I've seen say it's more than a millimeter per year. So it's about a third of the sea level rise we've seen is from the melting of mountain glaciers. There is a big question with some of these glaciers as to whether the water runs into the oceans or not, or whether it gets stored on the continent somewhere. Like the Himalayas is a place where I think a lot of the water is being stored in aquifers around the Himalayas and not making it to the oceans. So you have to be a little careful how to interpret that. But the mountain glaciers are certainly a large effect. And these are glaciers outside of Greenland and Antarctica. With the major ice sheets, I think it's helpful to think a minute about ice sheets dynamics and how the mass balance works. So these ice sheets are, in places a mile or two thick. It's a huge amount of ice, which is why, Greenland has 7 meters of ice locked up in it. And you have to look at what we call the ice sheet mass balance, which is the difference between how much precipitation you have coming into the ice sheet. So you have snow that's accumulating on the ice sheet and compacting and forming ice, and that ice then flows out to the edge of the ice sheet, calves off with usually at the outlet glaciers along the coast, and then goes into the ocean. And so the mass balance is looking at the difference between what's coming in and what's going out. And so that's a process that's always occurred. It's a natural process. And when you have the ice sheets start to contribute in a positive way to sea level change, it's because the ice sheet's getting out of balance. So you have more ice going out via the outlet glaciers than you do, or from melting, say, or than you have coming in from precipitation. So now I'm going to show you a video that was put together by NASA, and I don't know if Waleed showed this the other day, but it's a fascinating video, so it's worth seeing again. This is going to look at Greenland, and it's going to zoom in on Jakobshavn, which is one of the major glaciers along the coast of Greenland here. And I'll be talking a little bit about Greenland here in a minute. So but you can see here the calving front of the glacier, and here are the velocities from Landsat images, satellite images that show you how fast the ice is moving. So you can see it's slow out here, but then it accelerates coming down the outlet glacier, and this is the ice fjord that's outside the calving front. But you can see here, it shows how the calving fronts moved back over the last 100 years and very rapidly over the last decade. We see the velocities here have increased they nearly doubled in the last decade. And it's almost like a cork's been removed from Greenland, and so the ice has been flowing out much more rapidly. Now the colors you see here as we move out is the negative changes in the ice height that have been measured by ICEE over a similar time period, about the last 10 years or so. And so NASA has a big effort now to monitor Greenland and especially these outlet glaciers and try to understand the dynamics of the ice sheet. Now, while there, and you may have heard some about Connie Steffen's efforts too to go out to Swiss Camp every year and make measurements on the ice in Greenland. I was lucky enough to go out there once with him and see it. But I prefer to stay in my office and look at it with satellites. Although I would go back again if you asked me. So it's a fascinating place. But the satellite that we're getting a lot out of right now is this satellite called GRACE, the Gravity Recovery and Climate Experiment. It's 2 satellites that are about 450 kilometers in altitude, 200 kilometers apart, and there's a microwave system that measures the range between them, and it measures it really accurately. In fact, it measures that distance, 200 kilometers, to the accuracy of the diameter of a red blood cell, about a micron. And so as the mass of the Greenland ice sheet changes, that affects the orbits of these satellites and the distance between them. And to make a long story short, we can analyze that data and determine how the mass of the Greenland ice sheet is changing. And so that's the next slide here. This is showing mass changes over about the last 7 or 8 years. The satellite was launched in 2002, so I don't have a lot of data, but we're seeing a lot of ice mass loss along the coast of Greenland here. Here's the ice mass loss at Jakobshavn, which is I just showed you in the movie. Here's all of Greenland averaged together. And wherever you look, there's ice being lost, and it's equivalent to about 0.6 millimeters per year of sea level rise right now. There's a movie here that my friend John Warr made, and I want to show it to you because it really illustrates this. So I'm going to click here, and I want you to watch as it starts in the beginning of 2003, and watch as it goes through the years and what happens to the ice. Let's go back here. Okay, so it in the southeast moves up the coast, then moves up the west coast. So that's what Grace has seen over the last 7 years or so. So that was the movie, and I just have a few more slides here. One is the same thing's happening in Western Antarctica. This is again Grace observations. It's about a 0.5 millimeter a year of sea level rise as well. So the 2 ice sheets together are more than 1 millimeter per year of sea level rise over the last few years. The Alaskan Glaciers can also be observed from Grace. We're seeing melting there, although that's leveled out somewhat. Not seeing quite as much melting in the last year as we did before. So GRACE is just this great tool. I could talk all day about it because there's a lot of other things it measures that are interesting, but got to stay on the subject here and review the sea level budget based on the numbers that I've shown you. I didn't talk a lot about thermal expansion, but that's actually not measured from satellites usually. It's measured from ships at sea with instruments in the ocean. But we see about 1 millimeter per year sea level rise from thermal expansion, heat going into the oceans. About 1 millimeter per year from mountain glaciers, about a 0.5 millimeter a year from Greenland, and a 0.5 millimeter from Antarctica. These are all rough numbers, but when you add them all up, they all add up to about 3, say on the high side of 3 millimeters per year of sea level rise, which is about what we see from the satellite altimetry. So we talk about the sea level budget. We talk about closure of that budget. The closure is you measure sea level rise, you try and figure out what's contributing to it. You figure out what those numbers are. If they add up to what you're seeing, then you kind of close the budget. If you haven't, then you've got more work to do. So it's even been speculated from this GRACE data that the melting of Greenland and Antarctica might be accelerating, because you can see they're not really following a straight line. They're following more of a curved line, which would indicate there's some acceleration going on. And I think it's very early to be interpreting 7 years of data in terms of acceleration, but nevertheless, it's a useful thought experiment. If these accelerations were to continue, then by 2100 we'd have about 40 centimeters of sea level rise from both Greenland and Antarctica, so 80 centimeters total. Now I don't really think these accelerations are that accurate right now, but I think it's in terms of thinking about whether a meter is possible by 2100, most scientists think that it's well within the realm of possibility. So, which is interesting, because if you look at the last assessment of the IPCC, the International Intergovernmental Panel on Climate Change, the 4th assessment, that was a pretty controversial assessment in terms of sea level, because their highest sea level rise numbers were between 26 centimeters and 59 centimeters for one of the kind of the worst case scenario here. But they had a very important caveat here, which they said model-based range excluding future rapid dynamical changes in ice flow. So here, that was 2007, here is 2010, and we already see rapid dynamical changes in ice flow. So, so the next assessment, which will be out in 2013, will certainly have some different numbers in it. And part of the reason that these numbers are so low is because they felt like the science wasn't really there yet to support more accurate predictions. And I think there's more out there right now. In fact, right after this assessment was released in 2007, sorry about that, there was this paper that came out from Stefan Ramstorff, which used some empirical projection techniques. I won't go into the details here, but he was finding a much higher rates of sea level rise than the IPCC published in their report. So this shows the observations from the tide gauges. The green line here is from the satellite data, and then these are the projections for 2100. And so you can see a meter here is well within this range. And there's been a number of studies that have been published since based on these type of projections. And so here are the IPCC projections from 2007. And all these are different studies of what potential future sea level rise will be. They're all similar techniques, so we need to be a little careful about how we interpret them. But they all show a meter by 2100 as being within the range that we might think will happen. So the last point I want to get to here is I mentioned this effect of the ice on the edge of the ocean. So this is the predicted regional patterns in sea level rise if you melt mountain glaciers, Greenland, and Antarctica. And you can see if you melt Greenland, right in the vicinity of Greenland, there's actually negative sea level change slightly because you remove that mass and sea level actually falls around the coast of Greenland. Same thing around the coast of Western Antarctica. But you actually see more sea level rise away from these large ice sheets because that effect's not there. So we do have to think about what the patterns of sea level change are. I mean, I get calls every once in a while from insurance companies that want to know, okay, what's going to happen in Florida or places like that. And the science really isn't there yet, but we know enough to know that there's going to be big regional variations. The global mean doesn't give the whole story at all. So 1 meter of sea level rise, that's what New Orleans looks like, 1 meter of sea level rise, just what they need right now. And on top of that, in New Orleans, remember I mentioned at the start that land motions are important. These are satellite measurements of vertical land motion in the area of New Orleans, and these are units here of millimeters per year. So they're seeing land subsidence that's 3 times the rate of current sea level rise. And so places like New Orleans, the land subsidence is going to be an important additional effect. So, and then you look at Florida, that's a meter of sea level rise in Florida. Obviously, that's a major effect on Florida, but 6 meters would be even worse. That's where we think we're going. The 6 meters is we just don't know when that's going to happen. Whether that's 100 years or 1,000 years, we don't know when that's going to happen. I think that, you know, for sake of argument, I think by 2100, the picture probably looks more like this, a meter of sea level rise by 2100. That's what most scientists are saying. I'll know, on Friday, I'm going to a meeting it's an IPCC sea level workshop when all the experts in the world are getting together, and I'm sure this is one of the things that's going to be an item of discussion is not only what we think, because a lot of us think a meter is possible, but what can be scientifically justified, and those can be different. The science is still trying to get a handle on this and on what the spatial variations are. So I'm not gonna go through the summary here because I think I've covered all the points, but if you have any questions, be happy to take them.